So please mute yourself. So today's topic is diode resistance and diode capacitance. Diode resistance and diode capacitance. So in our previous class, we have seen about diode current equation. We have seen diode current equation and how currents in diode are flowing under bias conditions. Under biasing conditions. So this is the current I equal to I naught into e power v by vt minus 1 is the amount of current which will flow in a semiconductor, right? Where here V represents voltage, V across diode, Vt represents thermal voltage, Vt represents thermal voltage, right? So in some texts, in some textbooks, this equation is written as I equal to I naught into I equal to I naught into I equal to I naught into e power v by eta vt minus 1 అని ఉంటుందండి. Eta vt minus 1 where eta is a constant and the value of eta equal to 1 for germanium and the value of eta is 2 for silicon. Therefore, I equal to I naught into e power v by eta vt minus 1 is the current. Okay, is the current where I naught is reverse saturation current. Where I naught is the reverse saturation current, means it is the maximum current which flows when diode is reverse biased. Okay, so I naught is the reverse saturation current, and if V is the voltage across diode, and eta is a constant, and its value is 1 for germanium, and its value is 2 for silicon, right? Vt is thermal voltage, Vt is thermal voltage, Vt is equal to kT volts, Vt equal to kT volts, okay, where K is here Boltzmann constant, okay. Here I can write Vt equal to, I can write it as kT, okay, where K is Boltzmann constant, okay, kT volts, okay. Since Vt is a thermal voltage means the voltage which occurred due to rising temperature, okay, it's called thermal voltage, equal to kT. K is here Boltzmann constant and its value is 86.2 into 10 power minus 6, 86.2 into 10 power minus 6 electron volts per degree Kelvin, and T is the temperature in degree Kelvin. Okay, so I will get Vt equal to kT volts. In it is also written as Vt equal to k bar T by Q, k bar T by Q, where k bar is also Boltzmann constant, but it is expressed in joules per degree Kelvin. I think its value is 1.386 into 10 power minus 20, 10 power minus 19, 10 power minus 19 joules per degree Kelvin. I think so. Okay, so it's also written as k bar T by Q, means k bar equal to k into Q, such that k equal to k bar by Q. Okay, and it is also written as T by 11,600. Okay, it's a constant. Okay, 11,600 means if you substitute the value of k bar by Q, then Q is the charge. Q equal to 1.6 into 10 power minus 19 coulombs. Okay, all these values, I think uh, you are familiar with in physics, first year physics. Okay, and it is also equal to, it is also equal to dp by mu p, and it is also equal to dn by mu n. Okay, dp by mu p, dp by mu p, and is also equal to dn by mu n, where dp is the diffusion constant of holes. It's d suffix p and d, but I'm not able to write here d suffix p in this GeoMap. That's why I have shown you here like this. Okay, dp means diffusion constant of holes, mu p is the mobility of holes, dn diffusion constant of electrons, mu n mobility of electrons. Okay, so if you see, uh, mobility of electrons is greater than mobility of holes. Mobility of electrons is greater than mobility of holes. Okay, so now so now now mobility of electrons, mobility of electrons, okay, for silicon, for silicon, for germanium, for silicon and germanium and gallium arsenide. Let us take silicon is a semiconductor material, germanium is also a semiconductor material, and gallium gallium arsenide is a compound semiconductor material. Compound semiconductor material. Here gallium is group 3 element and arsenic is group 5 element. So I'm combining these two to form gallium arsenide. Okay, so so mu p, mu n means mobility of electrons, and mu p is the mobility of holes, mobility of electrons and mobility of holes. Okay, so if you see these things, then mobility of electrons in silicon, mobility of electrons in silicon is 1300. It's 1300. Okay, 1300, and the value of sorry, the mobility of holes in silicon is 500. Okay, and mobility of electrons in germanium, it is 3800, and the mobility of holes in germanium is 1800. These are the constants you have to remember while solving the problems. Okay, and the mobility of electrons in gallium arsenide is 4000, sorry, nearly 8500, and mobility of holes in gallium arsenide is 400. So what is mobility? What do you mean mobility? Mobility is the ability of charge carriers to move under applied electric field. Okay, mobility mu is the ability of charge carriers to move under electric field. Okay, and see here, when I applying some voltage, when I'm supply when I'm applying some voltage to a material, then what will happen? Electric field will be developed across that material, and that electric field is equal to, voltage applied by length of a semiconductor. Length of a semiconductor. So electric field is equal to volt per centimeter or meter. Volt per meter. It's expressed in volt per centimeter or volt per meter. Okay. So Volt per meter or volt per centimeter, right? So here, here due to this electric field, here, see here, it is capital VMI. It is capital V. Capital V means voltage here. Voltage by length of a semiconductor or material or conductor material, right? So now, due to this electric field, what will happen? Electrons means the charge carriers will drift in the material. So drift velocity, I call it V. I call it V is proportional to electric field developed. Okay, it is proportional to electric field developed. Therefore, if I take proportionality constant, then drift velocity of charge carriers is equal to mobility into electric field applied. Mobility into electric field applied. Therefore, mobility equal to, from this equation, I can write mobility equal to velocity by electric field. Velocity by electric field. So what about the units? Velocity, meter per second. Meter per second is the unit for velocity. Meter per second is the unit for velocity, and unit for electric field is volt per meter. Volt per meter. Okay. So what about the units now? What about the units of mobility now? Meter square per volt second. It is a gate question. Okay, in 2012 I think so, 2013 I think so, it was asked in gate question paper for 2 marks. So meter square per volt second is the units for mobility. Means, see here the mobility of electrons, mu n is mobility of electrons. Mobility of electrons is always greater than mobility of holes if you compare this chart. Okay, so mobility of electrons is greater than mobility of holes in this chart. Okay, and now and now uh, and now if you take the ratio of mobility of charge carriers, that is electrons to holes, means mu n by mu p. If you take mu n by mu p, if you take, okay, this value is equal to for silicon, it is nearly equal to 2 2.5, I think. Okay, it's nearly equal to, okay, it's nearly equal to 2.5. For germanium, if you take the mobility of electrons to mobility of holes, if you take the ratio mu n by mu p, means 3800 by 1800, if you take like this, it is nearly equal to 2. It's nearly equal to 2. And for gallium arsenide, if you take the ratio of mobility of charge carriers, electrons to mobility of holes, if you take, now it is nearly equal to 20. It is nearly equal to 20. Okay, so for high speed applications, I go for gallium arsenide, and for low speed switching applications, I go for silicon. Okay, I go for silicon, right? And now we are now moving on to our concept. Why I have told you this? Okay, about this equation, huh? Right? So today's topic is diode resistance. Diode resistance, right? What do you mean by diode resistance? What do you mean by diode resistance? The resistance offered by diode when it is biased is called diode resistance. Okay, is it clear for you? So what do you mean by the diode resistance? Diode resistance means the resistance offered by diode when it is biased. It is called diode resistance. So it is so you can see that it is dependent on biasing. I told you that, right? So diode resistance means resistance offered by diode when it is biased. So biasing is of two types. First one is forward biasing, and next one is reverse biasing. Forward biasing and reverse biasing. Practically speaking, practically speaking, for example, if I draw VI characteristics, if I want to draw these VI characteristics, practically speaking, the diode must conduct heavily in forward bias. The diode must conduct heavily in forward bias. This is voltage and this is current. Okay, the diode must conduct heavily during forward bias, right? This must be the ideal diode response. This must be the ideal diode response, right? And in reverse bias condition, it should not conduct anymore. In reverse bias condition, it should not conduct anymore. Means in reverse bias condition, in reverse bias condition, in reverse bias condition, if I take, it should not conduct anything. Means in forward bias condition, the diode must conduct heavily. That means resistance in forward bias is equal to zero. Is equal to zero. And resistance in reverse bias, I call it RR. Okay, I call it RF, forward resistance, right? In reverse bias, in reverse bias, the resistance must be equal to infinite. It must be equal to infinite. Okay, it must be equal to infinite. So reverse resistance must be infinite and forward resistance must be zero for an ideal diode. These are the characteristics of ideal diode. But we have seen in the characteristics of diode that that uh, I am getting some. See, this is the characteristic which is practically speaking. Okay, so this is the practical characteristics of a diode in forward bias. In forward bias condition, in forward bias condition, this is the practical characteristics of a diode in forward bias condition. And in reverse bias condition, very small amount of current flows through the diode, and after certain value, if I increase voltage much more, then due to due to avalanche effect, current increases rapidly. Current increases rapidly and diode will be blown off. Diode will be blown off. Okay, this is the condition. This is the practical characteristics. Okay, which I have shown this in this yellow color is the practical characteristics, and the characteristics which I have shown in blue color are the ideal diode characteristics. So, so till some voltage. Let us suppose till this voltage, diode is not conducting. Diode is not conducting. Okay, after this voltage, I am getting high currents. If I increase voltage, I'm getting high currents. Okay, this voltage is called cut-in voltage, V gamma. Already we have told this in characteristics of a diode, right? We call this V gamma. V gamma is the uh, voltage here. Till V gamma, I will get zero current. After V gamma, I will get high currents. Okay, I'll get high currents, right? So this V gamma is called cut-in voltage of diode. Okay, this is called cut-in voltage. Cut-in voltage of a diode. Cut-in voltage of a diode. cut in voltage of a diode. Okay, why this is happening here means already we have seen that in a semiconductor, half part of a material is doped with the trivalent impurities to make it p-type, and half part of semiconductor is doped with the pentavalent impurities to make it n-type. So what is happening here at the junction? At the junction, at the junction, there will be some there will be some barrier developing here at the junction. So this so at the junction, I'm getting some potential. I'm getting some potential. This potential, this potential, what will it do? It makes it makes for it makes impossible for charge carriers to move from both sides. So this potential is obstructing the holes to move from p side to n side and electrons to move from n side to p side. So here I have told you that this barrier width is offering some resistance. Okay, is offering some resistance, right? So that resistance is called forward resistance of a diode. That resistance is called forward resistance of a diode. Okay, if you draw the characteristics of a diode, if we draw the characteristics of a diode, right? If you draw the characteristics of a diode at any point, at any point, if you take, so if you take this point, if you take this point on the graph, if you take this point on the graph, okay, if you take this point on the graph, then mark voltage at that point and current at that point. Okay, so we all know resistance R equal to V by I. V by I, where V is voltage and I is current amount. So this is the value of V and this is the value of I. This is the value of I. So if you take any point on the graph and plot, if you take any point on the graph, so let us take this point now. Okay, if you take any point on the graph and if you take the ratio of voltage at that point and current at that point, current value at that point, then you'll get resistance. Okay, this resistance is called forward resistance. It is also called static resistance. It is also called static resistance. Okay, static resistance, right? This static resistance is is in the order of few ohms, in the order of few ohms, 10 ohms, 20 ohms, 50 ohms, 60 ohms, 70 ohms, like that. Okay, 100 ohms, like that. Okay, so this resistance is called static resistance of a diode. This resistance is called static resistance of a diode. Okay, now if you take 2 points on the graph, if you take 2 points on the graph, let us take this point and this point. If you take 2 points on the graph and if you take the voltage difference at that point, okay, so let's suppose this is the value of I, this is the value of I. If I extend, okay, this is I now, this is V, and if you take this point, this is the value of current. For see here, for a small rise in voltage, for a small rise in voltage, for a small rise in voltage here, the current increases much more in forward bias. The current increases much more in forward bias, right? For a small increase in voltage, there is a large increase in current. There is a large increase in current. Okay, if I take this point as V1 and this point as V2, and corresponding current at V1 is I1, and corresponding point at V2 is I2. Let us suppose if I take like this, I2 like this, then if I take ratio between the difference like this, okay, means V2 minus V1 by I2 minus I1, if I take difference of currents, and if I plot this also V by I, okay, if I take resistance like this, it is called dynamic resistance. It's also called AC resistance. It's also called AC resistance or dynamic resistance. Okay, it's called AC resistance or dynamic resistance. If I take only single point V1 by I1 or V2 or V2 by I2 like this, V2 by I2 like this, V2 by I2 like this, then I will get R1 and R2 values, resistance at different points. Okay, R1 and R2 values here. Okay, so this is called static resistance. This is called static resistance. This is called static resistance. Okay, so if you plot, so here, see one point here, R1 equal to V1 by I1. R1 equal to V1 by I1. Okay, what? So, what is V1 here? This point I call it V1. I have told you now. This point I call V2. Okay, this point I call V2. So V1 is the voltage and its corresponding current is I1. At voltage V2, corresponding current is I2. Means if you take this point, then resistance at point R2 is very less. But because the value of I2 is very high. Okay, it is in milliamps. In forward bias, it is in milliamps. And reverse bias, it is in microamps. Okay. So if I take this point, then I will get the value of R1 like this, V1 by I1, such that R1 will be greater than R2. R1 will be greater than R2. Okay, R1 will be greater than R2. R1 will be greater than R2. If I take this point, then I will get R3 kada. I will get R3 such that R3 is greater than R3 is greater than R1 and is greater than R2. If I go to the higher points, if I go to higher points on the graph, then resistance will decrease. If I come near to x-axis, then if I take a point near to x-axis, then the resistance is very high. Resistance is very high. If I take a difference of voltages like this, then the resistance which I got is called AC resistance or static resistance. This resistance I call DC resistance or dynamic resistance. DC resistance, sorry. This resistance is called DC resistance or static resistance. DC resistance or static resistance. This resistance is called AC resistance or dynamic resistance. Okay. And in reverse bias condition, if I take, actually at actually if I take ideal characteristics, the resistance must be infinite, but it is not the case in reverse bias. In reverse bias, what will happen here? if I increase voltage, if I increase reverse bias voltage, then what will happen? Junction width increases a lot. Junction width increases a lot. If junction width increases, what will happen? What will happen? Resistance at this point will increase. Resistance at this point will increase a lot. Okay, means in reverse bias condition, diode offers high resistance, not infinite, but a high value of resistance. So if I take any point on the graph, this point or this point or this point or this point or this point, so what will happen? For the large change in voltage, there is a small change in current. There is a small change in current. For a large change in voltage, there is a small change in current. This is changing current and this is change in voltage. Okay, this is delta I, this is delta V. This is delta I. Okay, so current is reducing here in reverse bias condition. Means resistance is very high in reverse bias. Why? Because if I give reverse bias more, if I give reverse bias more, then what will happen? Junction width increases a lot. Junction width increases a lot. If junction width increases a lot, then what is the phenomenon? Resistance at the junction will increases. So what will happen? It obstructs much more the flow of charge carriers. So the holes can't move from p side to n side, and electrons can't move from n side to p side. This will not happen. This will not happen. So what will be the resistance? Very high resistance. After that, after some voltage value called breakdown voltage, or or it is also called um, avalanche breakdown voltage. Okay, avalanche breakdown voltage. What will happen if I increase reverse bias voltage? What will happen? More number of charge carriers come outside. Why? Because due to thermal agitation, that tends to vibrate. They tends to vibrate, and more number of charge carriers will move due to thermal agitation, so that current will be increased a lot. Okay, after this condition, resistance is very less. Okay, these are the practical characteristics of diode. Is it okay for you? అర్థమైందేమో? Any doubts? Okay, you're not answering. So DC resistance or static resistance, it is defined as ratio of voltage to current. Just now I told you R equal to V by I kada ante in forward characteristics of P and diode. Okay, and next one is dynamic resistance or AC resistance. It is the difference. It is the difference in voltage by difference in current, delta V by delta I. Okay, delta V by delta I. Just now I have told you that if I go to the top of the graph, or if I take a point, if I take a point where the current is maximum, then the resistance will be very less, very less for this. Okay, and reverse resistance. Reverse resistance means it is the resistance offered by diode in reverse bias condition. It is very high. It is very high. Why? Because due to in reverse bias, what is happening? The junction width is increasing a lot, such that resistance will be very high, in order of mega ohms. That's why in reverse bias condition for a diode, the current is very less, in order of microamps. But in forward bias condition, the current is very high, in order of milliamps. Okay. So now let us move on to diode capacitance. Okay. Let us move on to diode capacitance. So what is diode capacitance? What is diode capacitance? See here, if I take you to the PN diode, if I take a PN diode, what will happen at equilibrium? What will happen? The holes which are majority charge carriers in P side, will move from P side to N side, and the electrons which are majority charge carriers in N side will move from N side to P side due to a process called diffusion. So what will happen? Here electrons will move from N side to P side, and here holes move from P side to N side. Okay, so what will happen? When electron move from N side to P side, then there is no electron here, there is no electron here, and there is no hole here. Both will recombine at the junction now. Both will recombine at the junction. So uncovering of charge carriers will occur. Sorry, covering of charge carriers will occur. So what will happen here at junction? A net positive charge will be developed at N side, and net negative charge will be developed at P side due to immobile ions. So here at junction, what is happening here? A barrier is formed. A barrier is formed here. Okay, this is a barrier. So what is a capacitor? What is a capacitor? It is a కెపాసిటర్ ఎలా ఉంటుందండి? టూ ప్యారల్ ప్లేట్స్ ఉంటాయి. ఒక పక్కన పాజిటివ్ ఛార్జ్ డెవలప్ అవుతుంది, ఒక పక్కన నెగటివ్ ఛార్జ్ డెవలప్ అవుతుంది. అవునా కదా? ఒక పక్కన నెగటివ్ ఛార్జ్ డెవలప్ అవుతుంది. సో దీస్ ఆర్ సెపరేటెడ్ బై ఏ dielectric material or air. Okay, so here if I assume this a positive charged plate of a capacitor and this as negative charged plate of a capacitor, then I can assume this as capacitance developed inside the PN diode. Okay, inside the PN diode. Okay, if I reverse bias it, what will happen? If I reverse bias this, what will happen? If I reverse bias this, what will happen? More number of holes will move from P side to the negative terminal of battery, and more number of electrons will move from N side to the positive terminal of battery. So here depletion region width increases. Why? Because the holes are coming out. Okay, so here what will happen? At the junction, in reverse bias, the depletion region width is increasing a lot. Okay, this capacitance offered by diode in reverse bias is called depletion capacitance, or transition capacitance, or space charge capacitance. Okay, space charge capacitance. This capacitor. So I can assume that as a here I can assume it as a parallel plate capacitor, one with positive charge and second with negative charge, separated at a junction. Okay. So under reverse bias conditions, these holes which are majority charge carriers from P side will be attracted towards negative terminal of battery, and electrons which are majority charge carriers in N side will move from N side to positive terminal of battery, such that depletion region width increases and here capacitance occurs. Capacitance forms here in reverse bias condition. This capacitance is called transition capacitance, or depletion capacitance, or space charge capacitance. Okay, Depletion capacitance means what will be depletion region? This is called depletion region now. This is called depletion region. What do you mean by depletion region? The region which is depleted by charge carriers is called depletion region. ఏ region లో అయితే ఫ్రీ చార్జ్ క్యారియర్స్ లేకుండా ఉంటాయో మనం దాన్ని ఏమంటాము డిప్లీషన్ రీజన్ అంటాం అనమాట. సి ఫర్ దిస్ అయాన్ there is a free charge carrier. For this ion there is a free charge carrier, but here for this ion there are no free charge carriers. For these ions there are no free charge carriers. These ions are depleted with charge carriers. That's why the capacitance occurred due to the depletion of charge carriers is called depletion capacitance. Depletion capacitance. Okay. So this capacitance now we are going to deal with. Okay, Nandi? So depletion capacitance, right? This depletion capacitance CT is also called transition capacitance. CT equal to dq by dv, rate of change of charge with respect to voltage. Okay, dq by dv. Q equal to cv kadandi. Q equal to cv, c equal to q by v. So right, see here, if I increase voltage, what is happening in reverse bias? Depletion region width is increasing, means more number of charges are accumulating at the junction. Okay, so this rate is changing. That's why I'm applying here dq by dv. Dq by dv, right? So let us suppose this is a PN region. This is a PN region. This is a PN junction. One side is doped with P type and second side is doped with N type. Oh, one topic I forgot, Amma. That is unequal doping. I will tell you tomorrow. Okay, unequal doping. Okay, means if for example, if N side doping is heavier than P side, means actually for a semiconductor, for a PN diode, half part is doped with trivalent impurities and remaining half part is doped with pentavalent impurities. Is it right? So till now we have seen the doping concentrations on P side or and N side. Doping concentrations on P side and N side are equal, such that what is happening at the junction, the width of depletion region is same at N side and also at P side. But for unequal doping, for example, if at N side, if doping concentration is heavier than P side, that is called N plus region. N plus region means heavily doped N region. If I write it as P plus, it is called heavily doped P region. Heavily doped P region. So if any one of the sites is heavily doped, then electrons more, see here in this example, N side is heavily doped. That's why I called it N plus region. So what will happen here means there is a lot of availability of electrons here. Okay, so what will happen? More number of electrons will diffuse from N side to P side. That's why depletion region width in P region will increase. Since P side is not highly doped, then less number of charge carriers will move from P side to N side. That's why depletion region width in N region is less. Okay, so in this example, N region is heavily doped than P region. That's why more number of charge carriers will move from N side to P side. Therefore, more number of charge carriers are diffusing from N side to P side. They will means more number of electrons are diffusing from N side to P side. They will recombine with holes here. They'll recombine with holes here. Therefore, uncovering of charge carriers takes place much more in P region. That's why depletion region width in P side is high. That's why WP is high. Since P side region is not that much highly doped than N region, so compared to N region, here P region has less number of holes than number of electrons in N region. Okay, which are majority charge carriers in both N and P sides. So this holes will diffuse not much more into N plus region. Okay, not much more into N plus region. That's why here depletion region width at N region is very less when compared to depletion region width at P region. That's why WP is greater than WN. Here I am taking uh, this Poisson's equation to derive this. Okay, I am taking Poisson's equation to derive this. Del square V by del x square equal to del square V. Okay, means del square V by del x square equal to, or d square V by dx square equal to E NA by epsilon. This is standard formula. I have to derive this, but this derivation is not relevant to this context. That's why just remember this formula. That's it. So integrate this equation two times on both sides. Okay, two times on both sides, right? Then this will occur. See here. So sorry, this is dx here. I am missing dx here. So dou square v by dou x square, if I double integrate this, dou square v by dou x square, if I double integrate this, then I will get one integral and one differentiation cancel, and second integral, second derivation is cancelled. Therefore, I will get v here, v here. Okay. So E is charge of electron, Na, Na here is a number of acceptor ions. Okay, and epsilon is electric field here. Therefore, E is constant here, and E charge is constant, doping concentration is constant. Therefore, this total is constant. So I am taking it outside. I am with 1 dx. 1 dx equal to x. 1 dx equal to x. Therefore, E Na by epsilon into x I am getting, and one integration I am remaining it with. Okay, since this is constant, I am taking it outside. I'm taking it outside. So I'm writing here like this: ENA by epsilon. I am with x. Okay, I am with x dx. X dx equal to x square by 2. Therefore, x square by 2 here it is. X square by 2 here it is. Okay, so if I double integrate this, then I will get this equation. Okay, what is V here? Voltage across diode. Voltage across diode. Okay, voltage across diode means voltage at a junction here. Voltage at the junction here. Okay, see here, voltage at the junction in the representation I am calling it VB kada. I am calling it VB kada. So I am replacing V with VB. I am replacing this V with VB. Okay, so I am with this equation now. VB equal to ENA W square by 2 epsilon. Okay. ENA W square by 2 epsilon. See what is A here? Oh, sorry. 1 second. Right. So here, correct. Will be equal to ENA omega square by 2 sorry, W square by 2 epsilon. Right. So why I am if I take this equation, this is x here. X here is x. X here is the width. X here is the width here. Okay, that's why I am replacing x. I am replacing x with w. Therefore, I am getting this equation ENA W square by 2 epsilon. I am replacing V with VB. Right? So what is charge density? Charge per unit volume. Why I am deriving this? Actually, why I am deriving this? Why? Because this equation is there for me, which is the basic equation. Which is the basic equation. Okay, to find CT, diffusion capacitance, sorry, depletion capacitance or transition capacitance, I am with dq by dt. So I need to find Q here. If I get the value of Q, then for any value of voltage, I will get capacitance CT. Okay, for this reason, I am finding Q, right? Charge density equal to charge per volume. Charge means Q per volume equal to E into NA. E into NA. E here means charge and NA means doping, acceptor ions. Okay, Nandi? Number of acceptor ions. So amount of charge E into NA. Okay, so here Q equal to ENA into volume, right? So if the diode has dimensions as W as width and its cross section area as A, then volume becomes W into area. W into area. So I'm getting Q here. Okay, what I want to find? dq by dv. This I want to find, dq by dv magnitude, because capacitance should not be negative. Okay, that's why dq by dv. This I want to measure. So I'm differentiating with respect to voltage. See here, Na is constant. Okay, E is constant. Area of cross section is also constant, but the width of depletion region is not constant. It is depending on voltage. That's why I'm taking out all the constants and I'm differentiating with respect to voltage V. Okay. So I'm differentiating with respect to V. So I'm getting this equation. Okay. So if I differentiate equation 1 with respect to V, what is equation 1 here? This is the equation 1. This is the equation 1, right? If I differentiate with respect to V, then I will get this value, ENA 2 epsilon pi dW by dV, dW by dV, which is the magnitude here. Okay. So dW by dV equal to, if I take this side, that is equal to epsilon by ENA W, because these two and these two are cancelled here. So dW by dV equal to epsilon by ENA into W, right? So dq by dV is AENA. Just now I told you na, AENA dW by dV, and I'm differentiating and I'm getting this voltage value. dW by dV equal to these two are get cancelled. So epsilon by ENA into W. This I am substituting in this equation. This I'm substituting in this equation. So if I substitute this in this equation, then CT, diffusion capacitance, this is CT kada, dq by dv. So dq by dv equal to A E N A. In the place of dw by dv, I am writing this epsilon by E N A W. Epsilon by E N A W. Okay, E gets cancelled, Na gets cancelled. Therefore, epsilon A by W. Epsilon A by W. This is the transition capacitance. This is the transition capacitance. Okay. So this is in reverse bias condition. Likewise in forward bias condition, it's called storage capacitance. It's called storage capacitance. It's also called diffusion capacitance. Why? Because in forward bias region, the junction is formed due to diffusion of majority charge carriers. Okay, that's why it is called diffusion capacitance. Okay, we will see it later in tomorrow's class. Okay, any doubts? Is it clear for you? Am I audible? Okay, in charts you are writing down. Okay, right. So from tomorrow onwards, you have to start a second unit. Okay.